All right, let's dive into one of the universe's most profound mysteries. We're going to peel back the layers on black holes, pulling them out of the realm of science fiction and into the world of real, honest-to-goodness, mind-bending physics.
Just imagine for a second, out there in the vast emptiness of space, there are these points of no return. Objects with a gravitational pull so ridiculously strong that once you cross their boundary, nothing gets out. Not a spaceship, not a planet, not even light itself, the fastest thing there is. And, it gets even weirder. As you get closer to one of these cosmic monsters, the very fabric of reality starts to warp. That steady, reliable tick-tock of a clock, it slows. Way down. Time, as you and I know it, just kind of starts to unravel. Sounds like something straight out of a movie, right? But here's the thing. Black holes are very, very real. So that brings us to our big mission today. What on Earth, or I guess what in the universe, is a black hole? Are they really these giant vacuum cleaners just roaming the cosmos, gobbling up everything they see? Could they be gateways to another universe? Or is the truth something far more bizarre and way more fascinating than we could ever imagine? Let's find out. To really get to the bottom of this, we have to start with a force we all think we know. The one that keeps our feet on the ground and the Earth going around the sun. We've got to start with gravity. See, a black hole isn't really a thing in the same way a planet or a star is. It's what happens when gravity, that force we feel every day, gets turned up to its absolute, most terrifying extreme. It is gravity's final boss. So how does gravity actually work? Well, Einstein gave us this amazing way to picture it. Think of the universe, all of space and time, as a giant, stretchy rubber sheet. Now, if you put a heavy bowling ball on it, the sheet dips down, right? And if you roll a little marble nearby, it doesn't really get pulled by the ball. It just follows the curve in the sheet. That curve, that warp in space-time, that is what we feel is gravity. The Earth makes a little dip in that sheet. The sun makes a much bigger one. But what if you could take something incredibly massive and squeeze it into an impossibly tiny space? What happens to that rubber sheet then? What happens when you don't just make a dip, but you literally puncture a hole right through the fabric of the universe? Well, the answer starts with the death of the biggest, most massive stars out there. Because the birth of a black hole, it's a story of total cosmic collapse. And it's a detective story that took physicists about 50 years to finally solve. The idea of a black hole didn't just appear overnight. It really was like a century-long investigation. It all started back in 1916 as just this weird mathematical quirk in Einstein's new equations. Then, scientists like Chandrasekhar realized that the biggest stars were basically doomed to collapse under their own weight. By 1939, Oppenheimer predicted this collapse would be so complete it would actually trap light. But it wasn't until 1965 that Roger Penrose proved it wasn't just some weird theory. No, black holes were an unavoidable consequence of gravity. And that finally brings us to what a black hole actually is. It's what's left behind after this unbelievable collapse. A chunk of space-time itself warped so intensely that to get out, you'd have to go faster than the speed of light. And nothing can do that. Okay, so we know how they're born, but what are they actually like? Come on, let's get a little closer to the edge, to the boundary that really defines what a black hole is. This boundary has a perfectly dramatic name, the event horizon. Now, this isn't some physical surface you could, touch. Think of it as a one-way door in space-time. Once you cross it, every single path leads in only one direction, straight to the center. There is no turning back. Here's a great way to think about it. Imagine you're in a canoe on a river that's heading towards a giant waterfall. Way upstream, you can paddle around no problem. But as you get closer, the current gets stronger and stronger. Eventually, you cross a line, a point where no matter how hard you paddle, the river is flowing faster than you can move. You're going over the edge. The event horizon is exactly that line, but for space-time itself. So, remember how we said time breaks? This is where things get genuinely bizarre. One of Einstein's craziest predictions is that gravity literally warps time, and near a black hole, that effect is off the charts. If you stayed a safe distance away and watched a friend fall toward one, you'd see their clock tick slower and slower until they just seemed to freeze at the edge, forever. But for them, as they slipped past that point of no return, time would feel completely normal. Okay,
I get it. This all sounds pretty terrifying. And it brings up that classic sci-fi image of the cosmic vacuum cleaner, right? So is that what's really going on?
And the answer is a big, resounding nope. A black hole's gravity is just like any other gravity. It all comes down to mass and distance. Here's the ultimate proof. If we could magically snap our fingers and replace our sun with a black hole of the exact same mass, you know what would happen to Earth's orbit? Absolutely nothing. We'd just be in for a very, very dark and cold ride. A black hole is only a vacuum cleaner if you get way, way too close. And look, this isn't just theory and speculation anymore. In just the last few years, our ability to actually see these things has taken a massive leap forward. As the team behind the Event Horizon Telescope put it, after they took a picture of the black hole in the center of our own galaxy, the evidence is now overwhelming. So how in the world do you see something that's by definition black? Well, you have to get clever and look for its effects. We watch stars orbiting what looks like empty space, moving at incredible speeds. We can now detect the ripples in space-time, gravitational waves, that get sent out when two black holes smash into each other. And, coolest of all, we can now take a picture of the shadow a black hole casts against the glowing hot gas swirling around it, right before it takes the final plunge. So we've seen how they form and how we know they're real. But now, let's go past the event horizon, metaphorically of course, and explore the deep mysteries that are hiding inside. This is the absolute frontier of what we know. Right at the heart of every black hole, there's something called the singularity. And this is where physics has to be honest and just say, we don't really know what it is. It's a point where our best theory of gravity, Einstein's general relativity, completely breaks down. The math just gives us nonsense answers, like infinity. Physics as we understand it just stops. And this breakdown leads to some of the biggest, most exciting questions in all of science, like what happens to the information of something that falls in? Is it gone forever, which would actually break the rules of quantum mechanics? Do black holes slowly leak radiation over trillions of years and just evaporate, like Stephen Hawking predicted? And what is really going on inside that singularity? Answering these might require a whole new theory of physics. So you might be sitting there thinking, okay, this is some fascinating cosmic stuff, but why should I care? What does any of this have to do with me? Because black holes are the ultimate laboratory. They are a stress test for the laws of physics. They're the place where our two best theories of the universe, one for the very big, one for the very small, smash together and break. So solving the puzzle of the black hole isn't just about understanding some weird object in space. It's about finding the next fundamental law of reality itself. They don't just bend light, they bend our minds and force us to ask, what comes next?